Good morning. Yeah, good afternoon. Today we're going to continue on our topic regarding buckling. By the way, I understand this class is between 12:30 to 1:20. If you have to eat, I really don't care. I know it's not no eating in the classroom. I can eat at the same time come for my lecture. I'm really not bothered. But please do not eat fried chicken. It's one of my favorite food. If you start eating fried chicken, you know what will happen? I will stop teaching. I will join for the food. Okay. Now, so today we're going to do centric buckling. January the 10th is CV. It's between 10:30 to 12:30, and it's in my office, ETV 216. Very clear. Questions? Yeah. Collect your beer. So those of you that I know it's so unfortunate that I have to teach you last term. It's whatever I owe you, okay? How many of you take 2Q last term, right? A lot of you, right? So whoever spot mistake on my board, okay, and I cannot remember how many, I'm going to buy about 96 cans. I'm not saying everyone will just come to GBOTs, okay? So come to my office, 10:30 to 12:30 in the morning. Are we clear? It's not PM, okay? PM will start drinking, I'll be so drunk I can't drive home. Are we clear? Okay? So come and collect your beer. Right. So we are going to carry on. You have seen, some of you have, yes, orange juice also. Okay, with alcohol, 2%, okay, no. The idea is not to get drunk, not to consume alcohol, am I right? Right? Yeah. Right, and master, we are a campus that no drinking is allowed, okay? But you know what? Once in a while it's fine. So we are going to apply the elastic curve. So what we are trying to do now, just to quickly recap, okay? On yesterday, what we have is we found the moment at point Q, okay? So we found the moment at point Q, which is M moment at point Q is minus Py, right? So then we are going to apply the elastic curve theory to determine the deflection. Okay, so we are again going to apply the elastic curve equation to relate the bending moment to deflection. Okay, so mathematically, I think all of you know the elastic curve theory, right? You learned in math before. Am I right to say that or no? You heard about it before, okay, but you have not seen how it works. Okay, so I'm going to show you how it works based on pure bending, right? Why bending is important? Because in buckling, we focus on what? Bending moment. Are we clear? Okay, bending moment induced by axial loading. Okay, so from here, so that's where I'm going to start our example. So we're going to apply the elastic curve theory. So we have a beam that has a gradient distributed load. We set up our boundary condition. Okay, so on the left-hand side, point A is x is equal to 0. Point B is x equal to L naught. We have Vm theta y. Now the sequence Vm theta y, I label the sequence for a reason. Okay, it's not just hey, what is this for? It's for a reason. So we have shear force, bending moment, slope, followed by deflection. And when in 2P, I believe you have done shear force and bending moment. Are we clear? Okay, then we're going to relate with slope and deflection. So from here, so the first thing we have to do, what we are going to do first is we are going to consider where we have a function which is equal to dv over dx is equal to minus omega as a function of x. Okay, so the thing now is, what is this minus omega as a function of x? So the next thing I'm going to draw, now if you have any question, just say excuse me, okay, and I'll pop my head out because I can't see you because of this screen. So we have a x on our x-axis, on our y is omega. So we have a gradient distributed load, and we know the distance from here to here. We have it as L0. And then where it stops over here, we know the amplitude over here. The amplitude over here is what we call omega naught. Okay. So if we're going to plot an equation for this straight line, right? So I highlight again, this is a straight line. So what we have is omega as a function of x is equal to omega naught over L naught x. Okay. So the first one, can you put this as our equation 1? Okay, so now we have formed our equation 2. Okay, so we're going to substitute equation 2 into equation 1. Okay, so what we have now is dv over dx. So this will be equal to minus omega naught over L naught x. Okay, so from here, we want to find V as a function of x, means the shear force as a function of x. We're going to integrate, and we're going to have minus omega naught over L naught x dx. So what we have over here is we will have minus omega naught over or x squared 2L naught plus by C1. This is our equation number 3. Okay. Now we have to have a constant C1 over there because we did not integrate with respect to any limits. Yes or no? Right? There's no limits. We did not have any values here or any values here. But what we have are boundary conditions. So we are going to now apply our boundary condition number 1. Okay, so boundary condition number 1, if you were to look over here, I'm going to label this as our boundary condition number 1. Boundary condition number 1 specify when x is equal to 0, shear force is also equal to 0. Okay, we have to use that because now we are dealing with what? Shear force. So once we have our shear force boundary condition number 1, we now realize that we can formulate when x is equal to 0, the shear force at 0 is also equal to 0. So when that's the case, therefore, C1 happen to be also be equal to 0. Yes or no? Right? So from here, again, we write out V as a function of x. This is equal to minus omega naught x squared over 2L naught. Okay, C1 is equal to 0. So this expression is our equation 3a. Sorry, before we go on to equation 3a, we can write this is equal to dm by dx. This is our equation 3a now. Okay. So now the next thing that we're going to do, we're going to determine our bending moment, okay, or our bending or our moment equation, and we're going to integrate minus omega naught x squared over 2L naught dx. Okay, so once we integrate this, it's really straightforward. We have minus omega naught x cubed over 6L naught plus by C2. Okay, so the outcome of this is our equation number 4. So again, once again, we have to look for our boundary condition. Okay, so we're going to apply our boundary condition number 2. And that is the only boundary condition that we can use because it's a function of moment. Yes or no? Okay, so when that's the case, over here, we're going to apply boundary condition number 2, where we have x is equal to 0. Moment at point 0 is also equal to 0. So therefore, from here, automatically, we can see that C2 is also equal to 0. Okay. So from here, I'm just going to draw a line, and then you can see the continuity rather than going to the next page. So from here, we can form the equation where m as a function of x now is equal to minus omega naught x cubed over 6L naught. Now, from here, we are going to, but before we go on, okay, let's look at these equations. Okay, you have your moment equation and you have your shear force equation. Okay. Okay. So question for all of you, by looking at your moment equation, more on the moment than the shear force equation, if you look at this structure over here, where will it break? You're going to fracture at point A, or you're going to fracture at point B? B. Why? You're right. It's point B. Why? Anyone, please? That's the maximum moment. So what if it's the maximum moment? Yes. Okay. Maximum stress. Yeah, maximum stress. Okay. So I've been expert witness 5 times now. I have to explain to a judge why that's the case. Okay. So I want you to use this explanation. You're right. Stresses are the highest, but so what? I don't know, have I drawn this with you guys? This is a building. Do not draw this, okay? And this is ETB. In 1 year, too many students failed the exam and Eugene decided to take his own life. Eugene is right on top of the, and this is the first floor, second floor, third floor, fourth floor, fifth floor, and there's the sixth floor. And when Eugene jumps, hoping that he has a strong heart, when will he die? Is it on the fifth floor that he will die? Yes or no? No. Is it on the fourth floor where he will die? Why he won't die on the fourth floor? Because there's nothing preventing him from what? I.e., something that's no stress from everything. But when will he die? Ground zero. Why? He cannot fall anymore. I.e., he cannot move anymore. Yes or no? Now, coming back to this structure, can point A move? Yes. Can point B move? Be clear. Okay. Anyway, whenever you restrict motion, you have to have a what? Action. Don't memorize it. Are you clear? Don't memorize it. You have to understand it. Are you clear? Okay. So from here, that is where maximum deflection will occur at, the no deflection will occur at point B, which we have written down here when y is equal to 0, means deflection is equal to 0. That's where higher stress will be acting upon. Okay, right. So after writing the moment equation, then we are going to let this be equal to what? This is our equation number 4a. At this stage, this is where we apply the what? This is where we apply the elastic curve theory. So from here, very easily, you just need to write down EI. You got d squared y over dx squared. Now this whole term is equal to minus omega naught x cubed over 6L naught. Okay. So what we're going to do next is we're going to integrate again. So dy by dx is also equal to EY what? Theta. Okay. And theta is a slope. So next, we just need to integrate minus omega naught x cubed over 6L naught. Okay, so when we integrate this, we will have minus omega naught x4 over 24L naught. Let me write my L properly. I'm scribbling, which is pretty bad. I do apologize. L naught plus by what? C3. Okay. So this is our equation number 5. So now, again, we have to solve for C3, and there's a way that we have solved for C3. This is where we have what? Boundary condition number what? Number 3. When you were doing math, the boundary conditions were given to you. Yes or no? Right? We were given math, the boundary condition. But the thing about structure analysis, okay, by looking at the structure like this, you need to make a decision to analyze the structure and work out the what? Boundary what? Okay, that's where math, you see the mathematical form, the procedure to solve. What does it mean in the what? Real world. Students struggle with this course because it's a heavy integration between what? Mathematics and what? Physics. Are we clear? I struggle with this course. Okay? Does not mean you have to struggle. So just follow my homework and follow my lead, you'll be fine. Okay, so you have to work out the what? Boundary condition. Okay, by looking at a figure. Okay. From here, we have a boundary condition. So we're going to substitute boundary condition number 3, which boundary condition number 3 states that what? When theta or when x is equal to L naught, okay, theta at L naught is equal to what? 0. Okay, so this is not so straightforward anymore. It's not a 0. So you have 0 on one side, and on the other side you have minus omega naught L naught